Welcome students in this course on heat transfer. This lecture is the introductory lectures where we are basically going to discuss what are the objectives of this particular course. Now if we see the syllabus, you will find that uh, we are going to study on the conduction heat transfer, and then we'll go to the radiation heat transfer, and after that we'll see the convection heat transfer, and within convection heat transfer we'll see the forced convection and the free convection. Then we'll go to the boiling and condensation, where basically during the phase change kind of heat transfer that happens, and then we'll see some of the heat exchangers. Heat exchangers are basically the equipments through which heat is transferred from one fluid to the another fluid. So finally we'll see the introduction to mass transfer. Definitely this mass transfer will be only introduced. We are not going to much detail of the mass transfer, but this mass transfer actually introduced in this course on heat transfer because the mass transfer having a lot of similarities with the heat transfer. If you see, the heat transfer equations and the mass transfer equations are very much analogous. So in many cases, with some modifications, you can basically apply the heat transfer equations to find out the mass transfer. Coming to the textbook, you can see I have suggested these two textbook for this particular course. The first one is Fundamentals of Heat and Mass Transfer by Incropera and others, and the second one is Heat Transfer, a Practical Approach by Yunus and Sengel. And these are very good books, though there are many other good books on heat transfer, but in these books basically you will find lot of practical problems with the practical data, and the problem solutions or the worked out problems are done nicely. That's why I have selected these books as the text. Now course objective and the course outcome. Okay, the course objective of this heat transfer course will be cleared as we move to the other slides gradually, because here in precisely, if we want to say that the course objective is that you can after learning this particular course, or after learning this particular subject, you will be able to design at least heat transfer equipments, because heat transfer equipments are the devices through which the heat transfer in different modes takes place. And if we know how to analyze theoretically of these different modes, we will be able to analyze the heat transfer process, and hence it will be possible for us to design the heat transfer equipments. So to give you a basic idea or the theoretical idea to how to calculate the different sizes or the shapes of the heat transfer equipments. So this is what we mean by the design. Okay, so and the course outcome is that we are expecting from you at the end of the course you will be able to design the heat transfer equipments. Since the heat transfer equipments, you will find sometimes it is handling the conduction heat transfer, sometimes it is handling convection, or sometimes it is handling radiation, or it may be possible that the combination of these modes are simultaneously occurring in the heat transfer equipments. So if you know all these kinds of processes, you will be able to design these heat transfer equipments, or you will be able to find out the different parameters those are required for the design of the particular device. Okay. Now let us start the discussion on the course. So first question that definitely come to your mind, that what the subject heat transfer deals with. The answer is like this, that you know that heat transfer takes place from a high temperature body to a low temperature body, or within a body from a region of high temperature to a region of low temperature. So this is what is the basic idea of heat transfer. So suppose here the temperature is T1, and at this point suppose the temperature is T2. Suppose this is one body and this is another body, and if these two bodies are connected, okay, so this connection can be either solid, this connection can be liquid, this connection can be gas, or if there is no connection at all, that means if it is vacuum, in that case also it is possible that heat transfer will take place between these two bodies. Okay, so we are going to discuss in this particular subject, heat transfer, that what is the rate at which heat transfer from a body of higher temperature to a body at lower temperature. So here we are considering, say T1 is greater, so it is expected that the net rate of heat transfer will take place from T1 to T2. Now, so in this particular subject, we are going to learn that how to calculate the rate of heat transfer. Rate of heat transfer takes place from a body at a higher temperature to a body at a lower temperature, and the mode of heat transfer can be of different kinds, like either conduction, convection, radiation, or their combination, but the sole objective is to calculate this rate of heat transfer. Now regarding the symbol that we are going to represent for the rate of heat transfer is small q. Okay, so small q is the symbol that we are trying to consistently use as the rate of heat transfer. So what is the unit of the rate of heat transfer? It's simply joule per second or watt. Okay, so watt is basically the unit of the rate of heat transfer, and the symbol for the heat, the total amount of energy, if that is in joule, then that is basically q, and this q dot, this particular quantity, is what is called the rate of heat transfer. So small q is the symbol that we are going to use in this particular subject. Okay, so that thing you have to remember. So you have understood that what this subject basically deals with. So in a simple sentence, if we say it basically deals with finding out the rate of heat transfer from a higher temperature body to a lower temperature body. Now definitely the question that will come to your mind next is, how is it different from the subject thermodynamics? Okay, to answer this question, first again I remind you that what we have seen in case of a thermodynamics. In case of a thermodynamics, if you remember, if this was a system and within that system the system is in equilibrium, let us consider. Okay, let us consider the system is in this state. Okay, so these are certain state variables x and y. Suppose this is the state of the system. The state of a system defined by its different properties. Okay, now some kind of energy interaction then takes place in terms of maybe heat and the work, and because of this energy interaction in terms of heat and work, we know that this system goes to a different state. That means it goes to a different equilibrium state. So in thermodynamics, what we have seen is that a system goes from one equilibrium state to the another equilibrium state, and in that process we are able to find out what is the net work interaction or the net heat interaction. Okay, or we are basically interested in finding out the how property changes when it goes along a particular path or goes to a different state, how the property will change from its initial state points. So these things were the main findings in case of a thermodynamics, but we have never tried to find out what was the rate of heat transfer. What was the rate of heat transfer that takes place? That we actually did not bother about when we have do the problems on thermodynamics. Okay, or we were not interested in finding out that how much time it will take for the system to go from this initial state to this final state. So how much time it will take. So finding out the time, or basically the same thing, finding out the rate of heat transfer that takes place. So these questions actually was not answered in thermodynamics. Rather, in thermodynamics we are basically deals with the equilibrium states, and you remember that when heat transfer takes place, it's no longer a equilibrium system because some kind of a temperature difference has to be there, and that's why it goes from one that is why the heat interaction takes place. So somehow these questions in thermodynamics is not answered. So this heat transfer is basically the extension of the thermodynamics, where we are going to find out the rate of heat transfer. So the basic difference between the thermodynamics and the heat transfer is we are now in a position to find out what is the rate of heat transfer in this subject heat transfer. But in case of a thermodynamics, we were actually not calculated rate of heat transfer. We have calculated the net energy interaction, maybe in terms of work or heat, or we have calculated the property changes because of a process. But in the heat transfer subject, we are interested in finding out how much time it will take to change its state, or what is the rate of heat transfer. Okay, so this is what is the basic difference between heat transfer and the thermodynamics. Now the next question that I am going to answer is, what is the importance of the study of heat transfer? So let us try to answer this question, and let us try to answer this question with an example. So already I have told you that this particular heat transfer subject, its importance is that if you know that, or if you can calculate that what is the if you want to calculate the heat transfer, in that case you have to know the mechanism of heat transfer. If you know the mechanism of heat transfer, then only it's possible that you can calculate what is the rate of heat transfer takes place. So that is why in the whole heat transfer course we are going to study in detail the mechanisms in detail, basically the conduction, convection, radiation, or their combinations, so that we can design the heat transfer equipments. Now again I am telling you that by heat transfer equipments we mean these are the devices through which heat transfer takes place from one fluid to the another fluid. Okay. Now in heat transfer equipments, by designing heat transfer equipments means maybe we want to find out what will be the size of the heat transfer equipment. Okay, by designing means we are interested in finding out what will be the shape of the heat transfer equipments, or maybe the design, suppose a particular size and shape is already available, we may be interested to know what will be the final temperature of the fluid which is passing through that heat transfer equipment. Okay, so these kind of questions will be able to answer if we know the process of heat transfer very well. Okay, let us take a very simple example and try to understand what we mean or what is the importance of the study of heat transfer. Here you can see in this picture, this is basically a radiator. Okay, here you can see the 4 engine cylinders are there. Here you see this is the 1, 2, 3 and 4. So you can see that within the engine cylinder pistons are moving. Okay, so here you can see this is the piston. The pistons are reciprocating within the cylinder, and you know the combustion takes place within the cylinder, and because of that huge amount of heat is generated, and those heat is required to be taken out from the cylinder wall. Okay, so to take out the heat from the cylinder wall, there is a jacket surrounding that cylinder, and through that jacket some fluid, maybe water or some other chemicals are sometimes mixed with the water, is passed, and then what that water or that particular liquid do is that it takes it takes heat from the engine wall. Okay, and it becomes hot. Okay, so after that water becomes hot, it goes to a pipeline. Here you can see through this pipeline, and it goes to the radiator, and in the radiator you see that there are small fins around the tubes. So within the radiator water flows, and around the tubes there are fins, so that the heat transfer from the hot water can easily takes place. And you can see there is a fan. You can see here is the fan, and let's take this color. Here you can see there is a fan. This is the fan, you see. So, and you see there are small fins are there, and through the fan basically air is passed through that radiator, so that heat is actually transferred from the water, from the hot water to the air. Okay, so heat is transferred from the hot water to the air, and that process actually is taking place within this radiator. And to enhance this rate of heat transfer, basically the thin fins are surrounded around the tubes through which the water is passing within the radiator. Then after passing through the radiator, when the water is coming out, it is now the cold water. It is no longer such a hot water. So then that water again goes to the cylinder wall, and again it takes heat from the cylinder wall, and the same process repeats. So this is the process by which the engine cylinder is cooled, and radiator is the device which is basically a kind of heat exchanging device or a heat exchanger where heat is transferred from the water to the air. Now, from the water to the air, how heat is transferred or what amount of heat is transferred, if you want to know, for that you have to know very well the process of convection very well. Okay, because majorly this particular heat transfer process is driven by the convection heat transfer. Okay, to be very specific, forced convection heat transfer. Now, so this is the so you can, if you want to design this particular radiator, so for that you need the basic knowledge of heat transfer or the process of heat transfer or the governing equations of heat transfer, so that you can calculate that depending upon the size how the rate of heat transfer will change. Okay, so this is an example. I hope from this example you have at least understood what we mean by the design of a heat transfer equipment can be done if we learn this subject, heat transfer. Okay, now coming to the another example. So let us try to understand in a better way that what kind of problems are encountered by the heat transfer engineers. So here you see in this example we have considered a problem of a steam pipe. So what is a steam pipe? Here you can see in industry you will find there are steam generators or called the boilers. So in the boilers you know that the steam is generated, and definitely to generate the steam at a very high pressure and temperature you need fuel. So it's a costly affair to generate steam. Now that steam is utilized in different way. It is not that this steam is only used to expand it in the turbine and produces work. Definitely this is one of the use that you have seen, but other than that in process plant at a different processes it is required to heat the different kinds of fluids, and for that steam is used for this heating purpose. Okay, so it is required to take that steam to different locations in the plant. Okay, so from the steam generator it is required through the pipe the steam to the different locations so that it can supply heat. So definitely the producing steam is a costly affair, and we do not want to lose the heat when it is transferred to a different point. So what is done? It is required to give insulation of the pipe so that the heat loss is minimized. Okay, so here you can see that the insulation that is given with the help of mineral wools. Okay, so these mineral wools are very common for the use of for the steam pipe insulations. Okay, so you can see this is kind of a fibrous structure, lot of airs are there, and as well as these are very much non-metallic fibrous kind of a thing, and that's why they having very low thermal conductivity, air having low thermal conductivity, so chances of conduction are very low. So in this way we can reduce the heat loss from the steam pipe. Now suppose we want to know that, let us consider a graph. Wait, let us consider a graph where in the x-axis suppose it is the thickness, this T indicates the thickness of the insulation layer, and in the y-axis suppose it is indicating the rate of heat loss, rate of heat loss. Okay, so If there is no insulation is there, that means if the thickness of the insulation is 0, then definitely the heat loss is very high. So let us do the blue, the heat loss is very high. Now as the insulation thickness increases, you will find that gradually heat loss will decrease. Okay, now suppose you want to know that if you want to restrict the heat loss to a particular level and you do not want that heat loss should not be more than that, suppose you want to restrict the heat loss to this much, heat loss cannot be more than that, then what should be the thickness of the insulation? Then definitely for that you can find out this will be the thickness. So you can calculate the thickness of the insulation if this one is known. That means if you want to restrict the heat loss not more than that. Or the problem may be reversed. That means suppose you know that the thickness is say this much. Suppose thickness is known and thickness is this much, and you want to calculate that then what is the amount of heat loss. Then the rate of heat loss you can find out from this graph. Okay, so to answer this kind of questions, that what is the rate of heat loss taking place if you know the thickness, or suppose you want to design what should be, or you want to calculate that how much thickness to be given so that the heat loss should not be more than this much. So for answering this kind of questions, you have to know the knowledge of heat transfer, because the curve that I have drawn initially with a blue line, this is what is the dictating line, and that particular line, the equation of that line definitely is the solution of if you solve the governing equation, and definitely this will come only if you know the heat transfer process very well. Here the process is specifically considering the conduction. So if you study well conduction, it's possible to get this solution, and if you plot that solution you will get this kind of a curve. And once you know this curve, to get this curve definitely you require the knowledge of heat transfer, and once you know the curve, then this kind of conclusions are not very difficult. Okay, so this is a kind of problems that heat transfer engineers solve. Okay, now let us see another example. So in this example you can see we have considered a steam condenser. Now what is a steam condenser? You know by the time that from the turbine, after the expansion in the turbine, the steam is in a superheated condition. Still it is in a superheated condition, or might be a small amount of water may be there, but anyway that steam is required to completely convert it into liquid, right? So in a steam condenser what happens, the wet steam or the dry steam, whatever that may be, that comes here. Okay, let us consider the wet steam which is coming here. If you remember the Rankine cycle, let us consider this is what is the expansion process. Let us consider the ideal expansion process takes place in the turbine. So this is what is the inlet, this is what is the inlet to the condenser, and in the condenser what is the process? The process is taking place like this. Okay, it's an isothermal process. Why it is an isothermal process? Because in this process basically only the phase changes takes place. There is only the latent heat is basically the transferred, and there is no transfer of the sensible heat. Okay, so from this TS diagram it is quite clear that how the process in the condenser takes place. So this is what is the process in the condenser takes place. So here you can see this is the position 1, that means the wet steam is coming into the condenser, and here you see the finally the water is coming out from the condenser. So if you call this point is 2, so this is basically the 2. Okay, so condenser is a device where wet steam is coming and only its phase changes, but there is no change of temperature takes place of this steam. That is clear. From 1 to 1 to 2 there is no change of temperature, only phase change takes place. Okay, now how this heat is exchanged, where this heat goes, or who is taking this heat? For that, definitely you have to supply the cold water. Okay, so here you can see the cold water is supplied, and that cold water basically you can see that these blue lines or the blue pipelines, you can see the small pipelines, blue pipelines, or rather the blue tubes you can see indicates the cold water is passing in this region, and surrounding that tube or outside those tubes basically it is the wet steam. Okay, so it is clear that there is a process of heat exchange between this cold water and the steam, okay, such that the latent heat of the steam is taken by the cold water, and definitely when that water coming out will become hot. So water become hot whereas it was cold. So here you can see the temperature of this cold water will increase when it will come out, and in this process this cold water will take heat, or rather the latent heat it takes from the wet steam, and in this process the wet steam changes its phase. This is what is happening in the condenser. Now if we want to plot the process what is taking place in the condenser, and if we try to understand the basic design of the condenser, here you see I am drawing a very simplistic picture. You just consider this is a pipe through which suppose the cold water is coming, say at T cold, and when it is coming out it is say T hot, and surrounding it, the outside it is the steam, and that steam is not changing its temperature. Actually it is not a single tube. What is the real situation? Real situation you can see in this figure. You see in this figure there are bundle of tubes are actually there. You can see lot of tubes are there. Okay, bundles of tubes are there, and surrounding those tubes basically the steam is passing, and through that tubes basically the cold water is passing. Okay, so this is what is the real situation, and we are just drawing a simple situation. So if we see the graph how things is going to happen, if you see let me draw this. So this line indicates the temperature of the wet steam, temperature of the steam which is say constant. Okay, temperature of the steam which is not changing when it is flowing through the condenser, it is only changes its phase. Whereas if you see this is what is the inlet temperature of the cold water, and the temperature of the cold water will gradually increase, and this is what is the temperature of the hot water. This is what is the temperature of the cold water. So this is what is the process that is taking place in the water tubes, and here it is what is the temperature of the steam which is constant. And it is quite clear that after this much of length, suppose this is what is the length of the tube that we are considering. Okay, so now what kind of problems we can answer if we know the heat transfer process, if we know the process basically dominated by the convection, definitely, and that convection process, if we studied very well, if we solve the governing equations, you will get this curve. That means this variation, how it is taking place. So in convection, basically we will find out this curve. Okay, when we'll go to the convection, we'll see that we'll be able to find out the equation of this curve. Suppose we know this is the equation. Now after that, what kind of problems we can solve? We can design the length of the heat exchanger. That means we can design the length of the condenser, so that exactly after this much of length, the temperature that is going out of the water, if that is limited, suppose the water, that is hot water temperature, suppose will be this much. If that is a particular condition given, then what should be the length of the tube? So if we want to find out this kind of a question, that what should be the length of the condenser, so that at the outlet the temperature will be a particular value. Okay, so for that we can solve from here, because we know the variation. If we consider this much of length, then TH will be this one. If we consider this much of length, then TH will be this one. If the length of the condenser is this one, then TH will be this one. So if you know the graph very well, you can find out that what will be the value of TH also, if you know what is the length. So problem can be of two ways. Either you know the length of the condenser and it is required to find out what will be the TH at the outside, or if you want to restrict the value of TH, then what should be the length. So in both way we can answer the questions. Okay, now coming to the next example. Here you can see the example is the heat treatment in electric furnace. Now heat treatment in furnace is required, you know, in furnace is a very common practice in industry, because for the manufacturing of different kinds of steels, you know that strengthening of the steel is very much dependent on the heat treatment process. Let us consider a very simple example. Suppose this is a furnace and there is some roller is there, suppose, and over these rollers the steel strips are basically passing continuously. Steel strips are passing, and here this is the furnace length. Now here it is air and here it is the furnace. Now the major dominating heat transfer is definitely is a radiation here in the electric furnace. Now suppose here the problem is, suppose this steel is moving with a particular velocity and it is coming at a particular temperature and it is getting some radiation heat. Majorly it is by the radiation, some heat is coming on the steel. So when it is getting out of the furnace, at that position, suppose we want austenizing temperature or more than austenizing temperature. Suppose we want to make a normalizing process, that it will be initially given to a temperature more than austenizing temperature, and then we'll keep it in the air. That means a kind of air cooling will do. Suppose we want to enhance properties by normalizing of a steel plates. So in that case, what kind of problems the problem is the design of the furnace. Maybe we are interested to know that what should be the length of the furnace, so that exactly outside its temperature will be just more than the austenizing temperature of the steel. So more than austenizing temperature for the normalizing process, you know, it is possible that what should be the length of the furnace that is required to be designed. Or it may be the problem that what should be the velocity. Suppose it is known that the length of the furnace is known, it is known that this much of temperature is required, then what should be the velocity of the steel strip that is required to send? Okay, so this problem also can be asked. Or suppose it is known that the length is this, it is known that the velocity is this, then we may be interested to know what should be the temperature at the outside when it is just coming out of the furnace. So these kind of problems can be encountered by the heat transfer engineers. Okay, so in these three examples you can see, in the first example we have considered, which is mainly dominated by the conduction, which is the case of insulation on steam pipe. In the second case you have seen, we have considered the condenser, where basically the process is dominated by the forced convection, and here in this example you can see it is mainly dominated by the radiation. Okay, let us see another example which is very relevant with respect to the recent times, that is electronic chip cooling example. See that many of the electronic components are nowadays used in industry for mechanical controls. Not only that, we are also using different kinds of electronic gadgets every day. So within these electronic components, what is actually there are a lot of chips, and within a chip basically what is there, actually lot of transistors are actually present. Okay, so maybe 1000-2000 transistors are there within a very small chip. Now these integrated chips, remember, because of these transistors produces heat, and it is again another thing that if the temperature of the chip is above a particular level, then that chip will damage. Or if the temperature above a particular level, maybe say 50 degrees centigrade or 60 degrees centigrade, then its life will not be very long. If the temperature is well below 50 degrees centigrade, then maybe you will get a very long chip life. But if the temperature on an average is say 65-70 degrees centigrade, it will not last very long. But if the temperature, suppose produced within the chip is say 130 degree, 140 degree, then definitely that chip will directly damage. Okay, so it is very important to remove the heat from the chip. It is required to remove the heat from the chip. Okay, so the thermal management of the electronic circuit is a very important area of study, and the heat transfer engineers do that particular study. So if we take a very simple example of PCB, let us consider this is a PCB, and suppose within that PCB there are some chips like what you can see in this diagram. Now how this can be cooled? This can be cooled maybe with the help of a fan. Okay, so with the help of a fan, basically we are creating the velocity. Okay, so air is blown over the air is blown over the surface so that heat can be taken out by the air, and definitely this process is the convection process. It is dominated by the convection process. So for this kind of a problem, the questions that we can answer, if we understand this convection process very well, then what should be the velocity so that the temperature of the surface should be less than say 50 degrees centigrade. We do not want the surface temperature of the chip more than 50 degrees centigrade. So what should be the velocity that is required? Okay. Or suppose you know, on the other hand, if this is the velocity that is known for a particular fan, then what should be the surface temperature of the chip? So this question also we will be able to answer. Okay. So these are the kind of problems that we are going to deal with in the heat transfer course. In the next lecture, we'll start discussing a very brief introduction of the conduction, convection and radiation. Okay, thank you.